This is 2021 question number 4. The main idea behind this question is going to revolve around these Newman projections. So if you're not familiar with these Newman projections, it's probably something you want to read about before attempting the question, or you need to look very carefully at these diagrams. The essential principle is that you look down the bond here. So this is your eye looking down the bond, and then you draw what you see. So these ones at the front, HA, B and C, and then D, E, F are all at the back. If you do have molecular models, they can be useful. So, for example, this is ethane, and like in the diagram, and we're looking down this bond. So if I hold it up like this, you can see that this is the Newman projection. So this is A, B, C at the front, or however they've got it oriented, A, B, C at the front. And then this is D, E, F at the back. And this dihedral angle, that's going to become quite important in the question, is the angle between one of the ones at the front and one of the ones at the back. So if I eclipse them and put them into the eclipse position, the dihedral angle is now 0. And then if I rotate that one at the back, the angle between here and here is 60. And if I keep going, the angle now between this one at the front and this one at the back is 120, and then go again, and now the angle between here and here is 180. So that's the basic principle. So there's lots of stuff for you to read there. I'm not going to read it. You can pause it and read it yourself. The question asks us the relative energy of the different conformations for a complete 360-degree rotation around the CC bond in ethane is shown in the diagram above. For the 5 dihedral angles shown on the graph, indicate whether ethane is in an eclipse conformation, write E in the box, or a staggered conformation, write S in the box. So just a reminder, this is a staggered, this is an eclipsed. And if you look from the side, in the eclipsed conformation, these are sort of in the way of each other. Whereas if I go into the staggered conformation, they are now avoiding each other. So this is going to be a low energy conformation, whereas the eclipse is going to be a high energy conformation. So this is very simply just going to be E, 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 S, S. So I'm just going to go ahead, write that in here. E, 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 S, S. Nice, easy 1 mark to get us started. Then, although theta can take any value between 0 and 360 for rotation around a bond, we often consider just 6 conformations, the 3 staggered and the 3 eclipsed. The diagram shows the relative energy of the conformations for rotation around the C2-C3 bond in methyl butane. Just so that we're clear what we're talking about, this is my model of methyl butane. Let me zoom out a little bit. Right, so I've got my 1, 2, 3, 4 carbons, and then I've got my methyl group on here. Now, when we're looking, you can see from the Newman projection here, I can see 2 methyl groups at the front and 1 methyl group at the back, which means that I'm going to be looking down this bond here. So if I rotate it round, so I'm looking down that bond, and then I just do a little bit of rotation, you can see that I've got the bond that I'm looking down, that one, and then I've got my 2 methyl groups at the front and my 1 methyl group at the back. I'm going to be rotating around this. That's going to be an eclipsed, staggered, eclipsed, staggered. Okay, and so I should be able to get myself into, let's see if I can get myself into this one here. In fact, I'm already in that one. I just need to rotate it around. So you can see, if I look down that bond, let me just orientate it properly. Okay, you can see that I've got these 2 methyl groups at the front, that's these 2 methyl groups, and I've got this 1 methyl group at the back. So that is my 1 position. Now, these methyl groups are a little bit, they are bulky, as you can see, that if when we rotate round, they're going to get in the way of each other, and that's why it's going to be a high energy conformation to be in. But in terms of visualization, they're a little bit cumbersome, so let me just switch them out. So for the rest of the question, if I get the model out, then you just have to imagine one of these green ones is a methyl group. So let me put myself back into this 1 position. That's my 1. If I just pretend that these green ones are methyls, I've got my methyl at the top, methyl here, and my methyl at the back, and then my other 3 are the hydrogens. Okay, so let's take a look at the question. match the 6 Newman projections of the methyl butane, 1 to 6, with the points A to F on the graph. Write only one number in each box. Now, the first thing to do is we know already that this is going to be eclipsed, 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 and this is going to be staggered, 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 because it's always an energy maximum when you're eclipsed and it's always an energy minimum when you're staggered. And then we can go through here and I can see, look, so this is staggered, 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 eclipsed, eclipsed, eclipsed. So these 3 eclipsed are going to be 1, 2, 3, these 3 staggered are going to be 1, 2, 3. And then really, the best place to start is to try and find the odd one out. So of the eclipse, there's one that's different from the other 2. So if I look down here, I can see that on this one, the methyl at the front and the methyl at the back are eclipsed. And here, the methyl at the front and the methyl at the back are eclipsed. But here, that isn't happening. The methyl, even though it's staggered, is always lined up with the hydrogen. So this interaction here and this interaction here is going to be very high energy, as I just showed you with the model, whereas this isn't going to be quite as high. So I know that this one must be 6. And then I can do the same here, because of these 3, one of them is slightly more higher energy. So here, the methyls are adjacent. That's a dihedral angle of 60 degrees. Whereas here, so here we've got the... so that's, sorry, if we look at both angles, they're both 60 degrees. So from the front car methyl to the back methyl, and from the other front methyl to the back methyl, they're both 60. Whereas here, from the front methyl to the back methyl, it's 60, but then the other front methyl is 180. And that's happened again here. So this front methyl is 60, but this front methyl is 180. So these 2 are the same, so they're going to be A and C, and they're sort of, these 2 are slightly further away, whereas here they're all bunched over to one side. So that's going to be number 1. So I've already got 6 and I've got 1. All we have to do now, like I said, is fill them in. But the problem is with this molecule, it's not a symmetrical molecule. So by which I mean, obviously it has some symmetry, but what I mean by that is that this and this aren't necessarily the same, and you're going to go round from here to there, and you have to get everything in order. Alright, so sorry if I haven't quite explained that quite clearly enough. Let me just get 6 here for you. So if I arrange my molecule in the arrangement for 6, which is that, where my methyls are eclipsed with hydrogens, then I can go that way to give me this 180, or I can go that way to give me this 180. And because we're increasing the dihedral angle along here, we have to make sure that when we start from this one, let's say for example if we started from 6, that we get the correct energy minimum, then the correct energy maximum in order. Now this is quite difficult to do without a model. I'll try and do it without the model first, and then I'll show you it with the model. So it makes sense to start from 6 or 1, so I'm going to start from 6. And then what I'm going to do is I'm going to rotate the front half. So you're rotating around this bond. I'm going to rotate the front one. So I'm going to keep the back atoms in place, and I'm going to rotate the front around like this. So imagine I take this and I rotate it round 60 degrees. So this one, this methyl, is going to be 180 to this methyl, and then the other methyl to the left is not going to be opposite. Okay, so let me get rid of that one. Okay, so what I'm looking for is my front methyl 180 to my back methyl, and then the other methyl to be to the left. So if I look at these 2 options here, all right, so I've got, this is my front methyl 180 to the back methyl, and then the other methyl is to the left. I know that's a pretty sketchy explanation. But if you look here, the front methyl is 180 to this methyl, but that's not this methyl. That's this methyl. So just again, so I rotate this around. So the front methyl is 180 to the back methyl, and then the other methyl is to this methyl's left. So it's sort of upside down a bit, but this methyl 180 to the back methyl, and then the other front methyl is to this methyl's left. So I'm going to put that one down as number 2, okay, which is very useful because that means that I can then put this one down as number 3. Okay, and then I'm going to carry on from the, I shouldn't have crossed that out really. So if I carry on rotating this front one round, what I'm then going to get is I'm going to get staggered. This methyl is staggered with a hydrogen, and then the left methyl is staggered with the methyl. So here you can see this is my front methyl, this is my front methyl, the right methyl here is staggered. Whereas here, this is my front methyl, this is my front methyl, now the left methyl is staggered. So that's going to be number 5, and that is going to be number 4. Okay, so if I go to 6 here, let me just get it into position, like that. Okay, and then what I did was I rotated it 60 degrees, and you can see that that I said was number 2, which you can see, you can pause it if you want, go through it slowly, you can see that I get that one. And if I rotate it another 60 degrees, I said that was going to be number 5, and you can see that matches up with number 5. I rotated it another 60 degrees, and I said that was like number 1, and you can see that is number 1. Rotate it another 60 degrees, and I get number 4, and you can see now it's my left methyl in inverted commas. Okay, I'm not 100% sure about this graph. This graph, if you're eagle-eyed, you'll have noticed that these graphs don't quite match, right? So this here, 0 degrees is an energy maximum, because 0 degrees indicates as the eclipse conformation, which should be an energy maximum. This here should really be shifted 60 degrees, because we should at 0 degrees be starting with energy maximum, but I mean I'm not going to commit myself to that. It's something to think about, but you can still get the answers. So the energy difference between conformations can be used to approximate the percentage of time a molecule will be found in each conformation by treating the interconversion between conformations as equilibria. So now we're going to move on from this three-dimensional, that's really exercising your visual, spatial manipulation ability in 3 dimensions in your mind. So we're now going to move on to something about equilibria. So for butane, we're going to assume that the molecule is always in one of 3 staggered conformations. We've got gauche 1, antiperiplanar, and gauche 2. The equilibrium has a delta G of this. Complete the table in the answer booklet. So, let me just complete my table. 5, no, sorry, this was 3, 6, 2, 3, 1, 4. Right now off screen. Okay, that. Sorry, can't read my own handwriting. 5, 1, 4. Okay. So now we've got to fill in this table. So if we look again at our conformations, we're basically, this is in equilibrium with that, which is in equilibrium with that. And we're being told that delta G for this one into this one is minus 3.63. So that is a spontaneous process, which makes sense because here they're slightly close together, whereas in the antiperiplanar they're as far away from each other as possible. Now, if this is a spontaneous process, this is going to be a non-spontaneous process, and it's the opposite of this. So we can just go for AP to G2, we can just go 3.63 kilojoules per mole. It's the opposite process. Okay, and then we're given G2 to G1, and this delta G is a state function. So we can take this and this as being the same. We can just assume this is going to be 0, or we can go, well, if this is from here to here is minus 3.63 and here to here is plus 3.63, then as a state function, then the sum of those is going to be equal to the overall. So that's just going to be 0 kilojoules per mole. And then we're asked to find K. So in order for us to find K, we're going to need to use this equation here. So we can rearrange that to get log K equals minus delta G over RT, and therefore K equals E to the minus delta G over RT. So a little bit of maths here. The only place you're going to slip up here, like in just your normal class, is that R is given in joules, whereas delta G is given in kilojoules. So just look out for that. So let's do this first one here. So K is going to be equal to E to the minus. I'm going to convert my delta G into joules. So I'm going to do minus 3.63 times 1,000 divided by 8.314 times the temperature, 298. So if I then put that in, this is going to be positive, so it's going to be 3.63 times 1,000 divided by 8.314 divided by 298, and then I'm going to do the exponential of that, and I get 4.328. Double check that 4.328 makes sense. It does, because we said this was a spontaneous process, so you'd expect the equilibrium constant to be larger than 1. As this is the inverse, now of course you can take this number and put it back into here, but it should make sense that as this is the inverse, this equilibrium constant is just going to be the reciprocal. So if I just do 1 divided by that, I'm going to get 0.231, and you can double check that by putting this number into here, which is just going to change the sign, but you will get that number back. If there's no difference, then the equilibrium constant is just A1, and obviously e to the minus 0 times anything is e to the minus 0, and e to the 0 is just going to be 1. Which I think a fairly straightforward question. See part 2 a little bit more tricky. We now have to calculate the percentage, which is always nice because we're just dealing with essentially ratios and have to work out any actual numbers. So the best way for us to think about this question is if we write it out. I'm going to write out all 3 equilibriums together. So I'm going to write, I've got G1 is in equilibrium with our antiperiplanar, which is in equilibrium with G2. Okay, and then I've said that this is 4.328 and this is 0.231. Now the way that I find this easiest to do is just to start putting in some numbers. All right, so let's suppose I had 1 as my amount of G1. If I had 1 as my amount of G1, remember K, this first K here, let's call it K1, is going to be the concentration of the antiperiplanar over the concentration of G1. And if I'm saying that's equal to K, which is 4.328, which is equal to my concentration of antiperiplanar, divided by my concentration of G1, but I'm saying my G1 is 1, this might be going a little bit fast, so if you lose track, just stop and rewind, all right? So what I've said is, I know this, I'm just going to pretend that G1 is 1, so I can say that 4.328 equals my antiperiplanar divided by 1, which means that my antiperiplanar is 4.328. Okay, so if G1 is 1, antiperiplanar must be 4.328. And by the same logic, if my antiperiplanar concentration or amount or concentration is 4.328, and this equilibrium constant is 0.231, then the amount G2 must be 1 by the same argument. Okay, so this is like a fictional equilibrium mixture composition. If I have 1 of this, I'll have 4.328 of this, and I'll have 1 of this. And I can check that because I know that the equilibrium constant for this is 1 to 1. So if I have 1 of that and 1 of that, that gives me K equals 1. All right, K equals 1, which I found back here. All right, so the total, I want to know the percentage of the time it's AP. Okay, so I can then just have down here, I can just say the total percentage composition of AP is going to be 4.328. That's my AP concentration divided by all of the others. So it's going to be 1 plus 4.328 plus 1 times 100. Okay, so if I do that, I get 4.328 divided by 2 plus 4.328 times by 100 gives me 68.4%. Okay, so there are, you know, generalized expressions in order to be able to do this kind of calculation, but I find it just very intuitive if you just put some numbers in, and you know, if you know K and you just pretend this one is 1. I could have chosen anything here. I could have chosen 100, I could have chosen 54. It doesn't matter as long as I follow the procedure through. Because it's asking for a percentage, it will always come out correct. Okay, so just a bit of light equilibria, which is fine. And then we're told we've got this acetylcholine. It's a neurotransmitter, and then we're given 6 different Newman projections. And we're told to group these conformations as sets of equal energy. All right, and it gives you examples of what to write. And importantly, don't miss this sentence here, include all conformations in your answer. So you need to have 6 numbers. Now I'm going to write on here, just to make my life a little bit easier, I'm going to write staggered, 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 eclipsed, eclipsed, eclipsed. Just so I'm not sort of looking around trying to find which ones are which. So I know that this can never be with this. All right, so staggered, staggered, staggered. Are any of these equivalent to each other? Well, here I've got the nitrogen and the oxygen 180. Here I've got the nitrogen and the oxygen 60. And here I've got the nitrogen and the oxygen 60. So 7 and 11 are going to be the same. And then 9 is different. And then I can look at my eclipsed. Here my nitrogen is not eclipsed with the oxygen. Here my nitrogen is not eclipsed with the oxygen. Here my nitrogen is eclipsed with the oxygen. So these two are the same. So I'm going to have 8 equals 10 and 12. So I'm just going to go ahead, write that as my answer. 7 equals 11, 8 equals 10, 9, 12. Done. Although it can adopt many conformations in solution, when it binds in muscle receptors, it has to adopt to a particular conformation. Drugs to treat various diseases seek to block this kind of bonding. All right. Many of these are rigid molecules, obviously, because you don't want them adopting different conformations. You want them to be stuck into one particular conformation, where the angle, the dihedral angle, cannot freely change. The drugs which most closely resemble the 3D shape of bound acetylcholine is usually bind most strongly receptors and are some of the most effective blockers. Fine. Okay. So what it's saying is, if the three-dimensional shape of this resembles the three-dimensional shape of this, then this will go into the receptor, and therefore it will block this from going into the receptor. Fine. That doesn't really, it's interesting, but it doesn't matter really for the question. So we have cyclopropane rings in these molecules are planar and have very little conformational flexibility. For each of the conformation, no, each of these conformations, 7 to 12, decide whether they are mimicked by W, X, Y, or Z. Some conformations may have more than one mimic, and some conformations have no mimics. So, does this look like any of these? Now, the really key thing to realise here, and it's great if you can realise it without the need for a model, is if you've got cyclopropane, on each carbon, I'm just going to write cyclopropane like that. On each carbon there are 2 groups. So what's missing from here is that you've got into the back there a hydrogen and into the back there a hydrogen. Okay, so immediately the most important thing for you to realise is that all of these are all of the eclipsed type. Alright, if we're looking along this bond here, then we are always in an eclipsed conformation, because this hydrogen eclipses with this and this nitrogen eclipses with this oxygen. So none of these are going to be comparable to our staggered conformations. So I'm just going to ignore those completely. Okay, and then here our nitrogen is staggered with our oxygen. Likewise over here, our nitrogen is staggered with our oxygen. Now I do have a cyclopropane ring here. Here it is, lots of ring strain, but you can see what I mean by this idea of, try and line up, this idea that we're always dealing with a eclipsed conformation. Okay? So, W and Z are equivalent, and they're equivalent to the one where the nitrogen and the oxygen are eclipsed. So if I look up here, where were my nitrogen and oxygen eclipsed? 12. So W is 12, Z is also 12. Then, very tricky, these here are not the same. In fact, these two molecules are enantiomers. They are mirror images of one another. You cannot rotate or turn this around in any way to get this molecule. So these two molecules are, even though you've got one going out of the plane, one going into the plane, one going into the plane, one coming out of the plane, they're not the same molecule. So easy to slip up here. So we need to find the one that's equivalent to this. So we're going to start at the nitrogen end. I'm going to look down the bond from the nitrogen end. So, because that makes sense, because all of these Newman projections all have the nitrogen at the front. Okay? So, we know it's not going to be 12. So we've just got to decide between 8 and 10. So here, you can imagine if you're looking down this bond, it's going to be, I'm going to sort of draw like a pretty sketchy Newman projection. That's going to be my N, and then that's going to be my O at the back. Alright, so it's sort of the nitrogen is coming to the right and the oxygen's going down to the left. And then I look up here and I look for that one. Alright, so I want nitrogen, remember, down to the right, oxygen at the left. That's not going to work there because that's nitrogen to the left, oxygen to the right. If you're you've got to sort of reorient yourself in your imagination. Whereas here, I've got the nitrogen going down to the right. Imagine that's right, then the oxygen down here to the left. Okay, so that is 8. And by the same reasoning, I can decide that this is 10. So then I have to fill in this awkward table. So W is 12, X is 8, Y is 10, and Z is 12.